Like cooties. Yeah, okay, here we go. Okay, Zach, flip to this page. Stop working on what you're working on. Tira, Daniel, up here. Yeah, I know, but you're looking the wrong way. Here we go. So, we're going to put it all together. We're going to combine the energy with the momentum. So, important things to remember. Momentum is conserved when things collide. We can use that. It means anytime you've got a collision, P initial equals P final is an option. We can use energy to analyze things like pendulums and curved ramps, because energy doesn't care what happens in the middle. It just cares where you are at the beginning and where you are at the end and the difference between those two things. Okay? So we can use energy to see what happens as things move, perhaps in weird ways. Using these together allows us to analyze more complex problems, a problem like this, assuming we break them up properly. So we're going to do 2 examples. We're going to briefly talk about a third, and then we're done. Here we go. The question says, here's my situation, find H. That's all you're given. Okay? And I love these kinds of questions. Yes, these are good questions. The only lesson I like better is the equivalent lesson at the end of the next chapter. That one is just, because then we add circular motion to all this, it just gets awesome. Okay, so find H. That's all we're told. So we're going to work our way backwards. So I've got an object that's rising. Okay, if I've got an object that's rising, what that means is this portion of the problem involves what concepts? Now, ignoring this, I've got an object that's rising to some maximum height. All we know is that this portion of the problem deals with energy. Okay? I'm going to have energy initial, perhaps plus work, depending on what the concept or the question outlines, is going to equal energy final. What kind of energy is present at the end here? There's only going to be potential, because at the maximum height, what's true? It has no more kinetic energy. At the maximum height, all the kinetic's been turned into potential. Okay? Before that happens, as we go backwards in time, this happens. I've got a bullet being embedded in a block. How do I analyze this portion of the question? A collision means momentum. Where I've got my initial situation equaling my final situation. What is the beauty? What's the purpose of the overlap here?
Your final momentum is your initial energy.
No, careful. You can't go. You're not making a direct conversion from final momentum to initial energy. But there is a direct link between these two. What's the link? Oh, sorry, who said that first back there? Abigail, was that you? Yeah, velocities. The final velocity from the momentum section of this problem is going to give us the initial velocity for the energy portion of the problem. And away we go. So let's do it. Okay, that is how you guys need to train yourselves to analyze these problems. They present you with a situation, it says find H. And I have a pretty good idea where you guys were, because I was in a similar situation. You know, however many years ago that I was a grade 12 student taking physics 12. I graduated in 05, do the math. So, you look at this question, you say, okay, well, this is where I'm starting. What the frig am I doing? That's not the way to approach a problem like this. The approach is to go backwards. Okay, I want the height. It's rising, energy, okay? And to work your way right to left, not left to right. So if you can train yourself to approach it like that, you can do this on your own. Once we've established what needs to happen, then we go forward to make it happen. So let's do it. We've got momentum. We know that at the beginning, we're dealing with a collision. So momentum initial equals momentum final. We know that we can't use energy here because we don't know about work or energy lost due to the impact. Momentum is going to conserve everything though. So let's use it. We'll have the the mass of the bullet times the velocity of the bullet plus mass of the block times the V of the block is going to equal the mass of the total. I'm not writing bull block this time. V of the total. The combined, when I say total, I mean the combined object. So mass of the bullet's 20 grams. I don't want grams, I want kilograms. So let's convert it up here, 0.02 kilograms. So it's going to become 0.02 times the velocity of the bullet we're told is 100 meters per second. All things considered, that's pretty slow. The velocity of the block is 0. So this whole expression is 0. So this is just going to equal the total mass, which is 4 plus 0.02. So 4.02 V total. So my velocity total, or the velocity of the combined object, is going to be 100 times 0.02 divided by 4.02 is like a half-ish. Rounded, it comes out to 0.5 meters per second. That is the speed at which this thing is going to move the moment after impact. So it's going to be 0.5 meters per second. That's going to give us the initial velocity for the energy portion. At the beginning of this thing, we're going to call this thing height equals 0 because we're concerned about the distance the object rises. This then, actually, if I were to draw it a little bit more level, this is the height we're asked to find. So now using energy initial plus work equals energy final. Is there any work being done on the pendulum? We're ignoring the collision, we're looking at the pendulum. Does the question make any reference to air resistance? No. Is there any other friction for the swinging pendulum? No. So because there's no mention of that, work is 0. It's an isolated system. So what kind of energy does this thing have initially? Purely kinetic. So KE is going to equal, what kind of energy does it have at the end? Just potential. PE. So half mv squared equals mgh. To make my life a little bit easier, I can cancel my masses. So h is going to equal v squared over 2g. I just moved some stuff around before I plugged in the values. So then the height of my pendulum, h equals, we know v, 0.5 squared over 2 times 9.8. What's the height? And I totally forgot to show you Mythbusters video yesterday. What's the height of the object? 0.013. Okay, so a easier way to picture that is to convert 0.013 meters into, so yeah, multiply by 100, 1.3 centimeters. So the block rose that much.
I'm surprised the floating dimension.
Well, it's a 4 kilogram block. Think of that like a sandbag. 4 kilograms is almost 10 pounds. It's like a bowling ball hanging there. The smallest bowling ball that you can pick up at the bowling alley, if I'm not mistaken, is 10 pounds. So this is a small bowling ball with a bullet getting shot. It's not going to swing it very high. Okay? But that's the process. The only way to bowl. Okay? Comments, questions, concerns? Flip the page, let's do another one. Oh no, it's just more interesting. It's not harder, it's interesting. Okay, a 5 kilogram mass initially at rest slides down a frictionless ramp reaching ground level. It then collides with a stationary 3 kilogram mass, and the masses then move apart at different speeds. There's no picture here, so let's draw it. No, here's what you've got. You've got a mass and a block at the bottom. Okay, this is a 5 kilogram mass and a 3 kilogram mass just kind of sitting here. I mean, you tell me what's going to happen. This guy's not moving. This guy slides down. When they make contact, the other one's going to bounce further ahead. And the 5 kilogram, either it will bounce back or it'll keep moving forward just a little bit. We don't know. We're told that everything is frictionless, yeah. So we don't necessarily know what's going to happen. We don't know if the 5 kilogram is going to bounce back or if it's going to move forward slower. We can find that out relatively easily. How do we break up this problem? We want to know what do we want to know? We don't actually have enough information to find anything in particular. Let's just start the problem. What is this initial part of the problem going to be dealing with? It's energy. How do you know it's energy? Yeah, because you have a falling object speeding up. So this portion of the problem here is all going to be energy. Eventually, they're going to collide. And then they're going to be moving off at separate speeds, yes, into the sunset. And then this portion of the problem is dealing with what? How do you know, Nathan? Yeah, because you have a collision. You got two objects that hit each other and are moving. When? That was just the question I was asking you. We didn't care about it. I just told you you have an object and its momentum changes. How? I don't care. Okay? So we can analyze this thing. Let's talk about energy. Energy initial plus work equals energy final. Tell me about that equation. Initially, there is only, okay, so we've got mgh. We're going to call this h. Why is there no work? Because it's frictionless. Love that. So that's going to equal what? How many half mv squared expressions do I need? The energy portion is just dealing with what? The 5 kilogram object sliding down the ramp. Okay? So we can cancel our masses. We could find v right away. V is going to equal the square root of 2gh. And now we've got a momentum problem. You know the final velocity of this 5 kilogram object is going to become the initial velocity in the momentum portion. The initial momentum of this 3 kilogram block is 0. This 5 kilogram object has a mass, or a velocity rather, of root 2gh. So 5 times the square root of 2gh plus 0 is going to equal 5 v of 5 final plus 3 v of 3 final. And because we don't have either of these velocities, this is as far as we could take the problem. But we took it pretty far without having any other values. One more very hand. I'm not even really going to do this one. We're just going to talk about it. Are there any questions about this? Okay. Then talk to me about this. All we're going to do is analyze. We're told all collisions are hit and stick, which means the objects are going to be combined. This is the setup. You've got a mass, and a mass, and the only thing you do is give this mass an initial velocity of v. How do you deal with the problem? Sorry, yeah, one of you at a time. Put your hand up or something. Nathan, speak. First, what happened? What are you going to do first? Okay, so you're going to do momentum of these ones, okay? So, momentum initial equals momentum final, because that's a collision. So right here, you're going to have M1 and M2. And they're going to combine. So I've got my initial setup and my final setup. Okay, someone else. What's the next portion of this? Zach, what are we going to deal with next? We're going to do energy up the hill. Energy initial plus work equals energy final. And at the end here, we're going to have an object that looks like this. Right before they touch, I'm going to have M1 and M2. And then we're having momentum. Why again, Joseph? There's another collision going on here. Momentum initial equals momentum final. No. They click together. Each click, click, click. And so now over here, we're going to have a giant mass of 1, 2, and 3 all combined. The final velocity here in momentum is going to equal the initial velocity for your energy portion. Oop, need to go back and I'll get this one. The final velocity here is going to become your initial velocity for momentum. And it's just alternating back and forth between these different concepts. And again, all you would be told is the initial velocity of the block, whether or not there is friction, and you'll be asked to find, you'll be given the height and then to ask the final V. You walking through this thing step by step and analyzing it is the hard part of this. Questions, comments, concerns? Looks relatively straightforward, yeah? Well, you haven't done any yet. I haven't assigned you any, Nathan. Flip the page a couple times, go all the way to page 201. Here's what I'm going to assign unto you. You're going to do 1, you're going to do 2. You're going to do 4. You're going to do 6. You're definitely going to do 7. And 11. There you go. That's what I've got for you. And you're right, it might not be overly difficult, Nathan. Or it might look like this.
Oh, that actually doesn't help anything. Without saying it. It just Everything physics looks confusing if you don't know the context.
I don't know the context.
There is wisdom in what you just said, Joseph, that you do not even fully appreciate yet.
Thank you for the
Okay, there is all of 6 minutes. Use this time. Either working on the questions from before or working on this now.